In lesson 4.5, we're going to kind of take a break from graphing polynomials, and you may have noticed in the unit title itself, there were two types of functions mentioned: polynomial functions, which we have been doing up until now, and rational functions. So this lesson is going to focus on rational functions. Um, so the big focus today is going to be looking at what do these do graphically? When we graph them, what do they look like? What can we expect? So all of our objectives today are going to build up to being able to visually display rational functions. So before we get started, we need to talk about, okay, what do I mean when I say a rational function? Well, we've talked about them in a previous unit, but just as a refresher, if something is a rational function, that means it can be written as a fraction. So the only difference is you're going to see variables in the denominator. So you might see something like this. That would be a rational function. You might see something like that would be a rational function. You have variables in the denominator. Now, what makes these kind of a pain in the butt to deal with sometimes is if you have variables in the denominator, that could cause issues for our domain. Remember, domain is all of our inputs, what we substitute in. So if I have a variable in the denominator, what number do I not want to end up being in the bottom? It's 0. So this is where we're going to have to be careful, and we're going to have to throw out any numbers that make the denominator 0, very much like we did in an earlier unit. So one thing that you're going to see when we graph rational functions are things called asymptotes. And think of asymptotes as almost imaginary lines. It's something you wouldn't actually see if you were looking at the graph. So here's what I mean by that. Let's draw a picture. So let's say we have our XY axis, like we're going to graph something. And let's say, let's go 1, 2, 3. Let's say there's a vertical asymptote going through 3. So I used a dashed line because we wouldn't actually see it. And what would happen, or what this does to the actual graph, let's say my graph ended up looking like this. So in blue could be a possible graph that we're going to see today. And think of the asymptote, or a vertical asymptote. I want you to think of it as sacred ground. In other words, the graph will not touch that line. It'll get closer and closer and closer and closer, but it will not actually touch it or cross it. The graph will never cross that vertical line. So think of it almost as a wall, or you know that song, nee, 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 can't touch this. You're not going to touch that line. Vertical asymptotes, since they're a vertical line, they will always be written in the form x equals and then a number, because they're a vertical line, and that's the form of vertical lines. On the other hand, we have horizontal asymptotes, and let me use black. These work the exact opposite. So if I had my coordinate plane, let's say our horizontal asymptote is up at 3. One possibility that I could see the graph do is maybe something like this. Notice both ends are going to get closer and closer and closer to the horizontal asymptote. Now with the horizontal ones, and this is where it gets a little bit tricky, I think of them more as a guide, because what ends up happening, and it's rare when this happens, but it can happen, the graph may cross horizontal asymptotes. So why can they cross the horizontal asymptote and not the vertical? When we do an example, I will tell you why that is. There is a reason for that. Horizontal asymptotes will always be written in the form y equals a number because they're a horizontal line, and that is the form of a horizontal line. So what I want to do first is an example where we just try and find the asymptotes, because today when we graph, we're going to put the asymptotes in first. They're kind of like our framework, and then we'll draw in the graph itself. So find the domain of the function, and then find the equations of the vertical or horizontal asymptotes if there are any. Sometimes there won't be any. So let's look at the domain first. So remember, domain is like our input, everything that x can be. So it might be quicker to figure out what x can't be. So my eyes would immediately be drawn to the denominator. That's where we're going to have issues. I do not want the bottom to be 0 because I cannot divide by 0. So kind of like what we did in an earlier unit, let's take the denominator and set it equal to 0 and solve it. Well, to solve this, I would just have to add 3. So that is the number I do not want. I do not want x to be 3 because that makes the denominator 0. So I'm going to throw that number out. So let's see if we can remember how to write the domain. If 3 is the only number I'm throwing out, then technically I can go all the way down into the negatives until I get to 3, or my little union symbol, 3 onwards. Remember, the more numbers you throw out, the more pieces your domain will be in. So now it wants me to find the vertical asymptotes. Well, the vertical asymptote has a direct connection to the domain. What did we say x could not be? 3. So what ends up happening, that is where the vertical asymptote is going to be located. That's where my wall is going to be located because I know the graph won't touch that. Now the horizontal asymptote is a little trickier. The horizontal asymptote, y equals, I'm going to tell you it's at 1. Well, how do I know that? Just by looking at it. There is a way to tell. And in just a moment, I will tell you how to figure that out right away just by looking at what they gave you. Let's look at the next one. Find the domain. So again, my eyes are drawn to the denominator. Let's set the denominator equal to 0. And we want to solve it. So what would I do first to solve this guy? I want to subtract 1. And now I want to divide by 4 to cancel out the multiplying. And what would be the last step to get x alone? Well, to get rid of the square, we would have to square root. Now I'm actually going to stop the train right there because I have a negative under a square root, which we know is an imaginary number. So that means, what that's telling me, the only thing that will make the bottom come out to 0 are imaginary numbers. So my domain, I don't have to throw anything out because there are no real numbers that will make the bottom 0, just imaginary. So everything is good. There is not a number that I can plug in for x and get 0 on the bottom. It's not going to happen. So then what does that mean about my vertical asymptote? If I didn't have to throw any x's out, there isn't a vertical asymptote. There's not going to be an imaginary wall that I can't touch. I didn't throw anything out. And the horizontal asymptote is going to be at y equals 2. How did I get that? You might be able to tell how I'm getting the horizontal asymptotes. On the next chunk, I'm going to tell you how I'm getting those, and then we'll come back to these and see if it makes sense. Okay, this section in your notes is going to be the gold part of the notes. You want to make sure you take really good notes here because these are going to be the steps that we use to actually make the graphs. So when I graph rational functions, the first thing I want to do, I want to look for vertical asymptotes. So this is where, you might have guessed it already, to get the vertical asymptotes, you just set the denominator equal to 0 and solve. The vertical asymptotes are going to be whatever makes the bottom 0. Whatever I have to throw out, that's going to be where my imaginary wall is. Now the horizontal asymptotes are a little trickier. I want you to picture a function, and I'm going to call it this. Okay, so let's say we have a function in this setup. Ax to the n over bx to the m. Okay? What I want you to think first, what happens if my exponent up top is greater than the one on the bottom? So I'm looking at the exponents, the highest exponents of each. If the highest exponent in the numerator is bigger than the one on the denominator, what that means is there will not be a horizontal asymptote. Well, why is that? Think about it like this. If I just show you with numbers, let's say I had 10 over 1, and then 100 over 1, and then 1,000 over 1, and I kept going. Notice as the top just keeps getting out of control, bigger and bigger and bigger. As I divide these, you'll notice my answers are just getting bigger and bigger and bigger and bigger. They're not getting close to anything, so there's not going to be a horizontal asymptote. Let's do this bottom one here. What happens if the exponent up top is less than the one on the bottom? So it's smaller up top than the one on the bottom. That means your horizontal asymptote is going to be at 0. Well, why is that? Well, let me show you with numbers again. So let's say I had 1 over 10, and then 1 over 100, and then 1 over 1,000. So this would be like 0.1, 0.01, 0.001. So notice as my bottom keeps getting bigger and bigger and bigger, what happens to my numbers? They're getting smaller and smaller and smaller, or you can think of it as they're getting closer and closer and closer to 0. And finally, what happens if the exponent up top and the exponent on the bottom are exactly the same? They're the same number. Well, if that happens, I want you to think of like the x's canceling, and you're left with the coefficients out front. So whatever a and b were, that would be the horizontal asymptote. So look back at these examples and let's see if we can figure out how I got my answers for the horizontal asymptotes. So this first one, let's look at our highest exponents. So my highest exponent up top was a 1, my highest exponent on the bottom was a 1. Since they equaled each other, they were both 1, I want to look at my a over my b, which there was 1s sitting out front. So if I took my a over b, that's how I got 1 for my horizontal asymptote. Look at the next one, the second example. The highest exponent up top was a 2, the highest exponent on the bottom was a 2. They were equal. If they're equal, I want to take a over b. Well, 8 over 4 is 2. That's how I got a horizontal asymptote of 2. If you're still fuzzy on asymptotes, we're going to work with them more in the next examples. We are not going to worry about this guy. Finally, intercepts. So we've done intercepts before, and they're going to work the same way as they have with other functions. To get the x-intercept, we want to put 0 in for y so that we can find the x's. To get the y-intercept, we want to put 0 in for x and then solve. Okay, so we're going to take all of this information now, and we are going to see if we can make graphs. So let's try it. So I want us to graph. We're going to find any asymptotes and intercepts, and we are going to state the domain. All right, lots of stuff here. Let's look at the domain first. So since I have a denominator, that's where my eyes are going to be drawn, because I do not want the denominator to be 0. So let's figure out what would make the bottom 0. If I solve that, I do not want x to be -3. That's going to make the bottom 0. So my domain there would be my domain. Everything but -3. Okay, the next item, the vertical asymptote, which I just abbreviated as VA. The vertical asymptote comes from whatever makes the bottom 0. It's the thing I don't want. Well, we already know that it's -3. So the vertical asymptote is going to be x equals -3. Let's go ahead and graph that right away. So I'm going to go to where x is -3, and I'm going to draw in a dashed line. Make sure it's a dashed line because we won't actually see it when we look at the graph. Okay, the next thing I want is the horizontal asymptote. Okay, horizontal asymptote. This is where I have to look at the highest exponent up top and the highest exponent in the bottom. Let me write it over here. Well, the highest exponent on the bottom is a 1. That's easy to see. But what the heck, there's no x's up top. Well, technically there is an x up top, but it's x to the 0. So let's compare them. I have a 0 up top and a 1 on the bottom. The exponent is higher on the bottom. If I look at my 3 horizontal rules, if it was bigger on the bottom, so that's rule number 3, so n is, the number up top is smaller than the one on the bottom, that means the horizontal asymptote is y equals 0. Let's go ahead and graph that. So a horizontal line going right through 0. Okay, we're not going to worry about the slant asymptote. And now let's find our intercepts. So to get the x-intercept, I'm going to put 0 in for the y. And remember, on this problem, g of x is the same thing as y. So 0 equals 6 over x plus 3. So now the question is, how do I solve for x? Well, probably the quickest way to solve this, to cancel out the dividing, I could times by x plus 3. Then I have to do it to the other side. So they cancel. 0 times x plus 3 is 0. I get 0 equals 6. What? There's no x left, and that doesn't make sense. Because this is complete garbage, there aren't any x-intercepts. So how does that help me with the graph? Well, I know when it comes time to look at the graph, it's not going to touch the x-axis. It will not touch the x-axis. That's why we're looking at the intercepts. Now let's do the y-intercept. To get the y-intercept, we're going to put 0 in for x. And I would like to simplify that. Well, that would be 6 over 3, which is 2. So we have a y-intercept at 2, meaning I'm going to cross the y-axis at 2. So let's plot that point. So on the y-axis, I know my graph is going to cross through that point. Guaranteed. So really, to make this graph, we need some more points. It's not enough to make the graph off of 1 point. So what I recommend doing, let's make a little table here. And we're going to plug some numbers into this table just to get a few more points. I don't care what numbers you pick to plug in. I personally will pick some numbers on the left of the vertical asymptote, and I will pick some numbers on the right. So my vertical asymptote was at -3. So I don't know, let's pick -5. So if x is -5, I want to know what is y. Well, if I quick plug -5 in for x, that would be 6 over -2, and 6 divided by -2, I get -3 out. Let's pick another one. Let's pick -4. If I put -4 into my equation, -4 plus 3 is -1, so 6 over -1 is -6. Now let's pick some points on the right side of the vertical asymptote. So maybe, let's pick -2. So if I plug -2 in, that would be 6 over +1, so 6. Let's do one more. How about -1? So if I plug -1 in, I'd get 6 over 2, so I get 3 out. I don't care how many numbers you pick to plug in, and I don't care what numbers you pick. We just need more points. So let's plot them. -5, 1, 2, 1, 2, 3, 4, 5, -3, so that point is right here. -4, -6, 2, 3, 4, 5, 6. -2, 6, 2, 3, 4, 6, and -1, 3. So I know these points have to be on the graph. The last thing that you might want to check for, and I know there's a lot to these. If you want one more thing to kind of help you figure out what this graph is going to look like, we could look at symmetry. And if we're going to check for symmetry, this is where, if this was my original function, if I replace x with a -x, like we did way back when, I can't really do any simplifying. Because I replaced x with -x and I didn't get the exact same thing out, and I didn't get the exact opposite out, this means this graph has no symmetry. If I actually make my graph, what you want to do is you want to pass through the points and you want to stick really close to the asymptotes. Think of them as magnets. So, right there, and we're passing through the points and we're being drawn towards the asymptotes, but we're not going to touch them. Now I said sometimes you will cross the horizontal asymptote. I know on this one, I'm not going to cross it. How do I know that? Well, since it's right on the x-axis, we said there's no x-intercept, so I know it's not going to touch it. They will never touch the vertical asymptote because that represents the thing that makes the denominator 0, and I can't divide by 0. So there is my graph. Oof. Let's look at the next one. Actually, no, this one I'm throwing out. So let's look at the next one. Yes, this is one I want to look at. So on this one, we want to do the same exact process. So let's first figure out the domain. So I'm going to focus on the denominator. And let's solve it. So I'm going to add 9. And then I'm going to square root. Make sure you have plus minus. So 2 numbers come out for x. So that means I'm throwing 2 numbers out. I don't want 3 and I don't want -3. So when I write my domain, the first number of those I would run into is the -3, or -3 to 3, or 3 to infinity. Right? We're just working our way up on the number line. So now we should already know the vertical asymptote. Remember, the vertical asymptotes are what make the denominator 0. Well, there's 2 things that made the denominator 0, 3 and -3. What does that mean then? It means I have 2 vertical asymptotes. There are 2 things that made the bottom 0. Let's graph both of those asymptotes. So 1, 2, we got 1 through -3. And we have 1 through 3. 2 of them. Okay, the horizontal asymptotes are where I have to look at the highest exponents. So the highest exponent on top is a 2. The highest exponent on the bottom is a 2. So what does that mean if they match, if they're equal? Well, if they were equal, which is option number 2 here, I take a over b, which is the coefficients out front. Well, a over b would be 3 over, there's technically a 1, so 3 over 1 is 3. So I have a horizontal asymptote at y equals 3. So draw that in. We're not going to worry about the slant one. And now I would like to find the x-intercept. So we're going to set our function equal to 0 and solve. So now how do we solve this? Well, the first thing I would do to cancel out this division, we can multiply. So they cancel. Anything times 0 is still 0. Now I would add 3. To cancel out the multiplication, we can divide. So I get 1 equals x squared, and then the last step would be to get rid of the square, so we'll square root. And be careful, make sure you have plus minus. So what does that mean? Well, it means I have 2 x-intercepts. I'm going to touch the x-axis at 1, and I'm going to touch the x-axis at -1. Let's plot those points. So 1 and -1. The y-intercept, let's put 0 in for x. And simplify, so 0 squared is 0, 3 times 0 is 0, so I'd be left with a -3 up top. On the bottom, 0 squared is 0, minus 9, I'd be left with a -9. I'd like you to simplify that, so if I divide 3, I would get a positive 1 over 3. So there's my y-intercept. So let's plot that, so just it's like 0.3-ish on the y-axis. Okay, now I would just like some more points so I have a better idea of what this graph is going to do. So I would pick some points on either side of my vertical asymptotes. So since this vertical asymptote on the left is at -3, let's pick like -5 and -4. Let's see what happens. So if I plug 5 in. I'll show you down here what's going to happen. So 3 times negative 5 squared minus 3. And then I have negative 5 squared minus 9. Let's do the numerator first. So negative 5 squared is 25. 25 times 3, 75. 75 minus 3, so the top becomes 72. On the bottom, negative 5 squared, 25. 25 minus 9, 16. I would like that fraction simplified. 8 will go into both. So after simplifying, the fraction becomes 9 over 2. Okay, if I plug negative 4 in, so I'll just keep this framework here, but this time I'm going to put a negative 4 in, and I want to see what comes out. So negative 4 squared, 16, times 3, 48, minus 3 is 45. And on the bottom, negative 4 squared is 16 minus 9, 7. And that can't be simplified. So 45 over 7. Let's see, what else could we pick? If you're not sure, let's pick negative 2, because that's on the other side. If I plug negative 2 in, let's see what comes out. So negative 2 squared is 4, times 3 is 12, minus 3, I get 9. On the bottom, that'd be 4 minus 9, negative, so I get a negative 9/5. So now looking on the right side where the asymptote is 3, let's do 2. I'll tell you, if you plug 2 in, doing the same process, you will get negative 9/5. And then I'm going to do a couple more yet. I'm going to do 4 and 5. Just to save time, if you plug 4 in, doing the exact same thing we were doing, it turns out you get 45 over 7 out. And if you plug 5 in, you get 9 over 2 out. If you wanted to know about the symmetry, if I take my original function, which was 3x squared minus 3 over x squared minus 9, and I replace all the x's with a negative x, watch what happens. If I clean that up, a negative x squared is positive x squared. Same thing on the bottom. Notice, even when I replaced all the x's with the negative x, I got the same exact thing out that I started with. If that happens, remember that means y-axis symmetry. If I would have got the exact opposite out, that's origin symmetry, opposite origin. Okay, let's plot our points and be done with this one. So negative 5, 1, 2, 3, 4, 5, 9 halves as a decimal is 4.5. So 1, 2, 3, 4, it's like right here. Negative 4, 1, 2, 3, 4, and then if you take 45 divided by 7, it turns out that's 6.4. 4, 5, 6.4-ish. Negative 2, and then negative 9/5. Negative 9/5 as a decimal is negative 1.8. So 1-ish, like right here. So then 2, also negative 9/5. 4 will be up at the same spot. Notice y-axis symmetry, so it's going to be a mirror image. And so then I know I'm going to have another guy here, y-axis symmetry. So now if I connect them, I want to make sure to just follow the asymptotes but pass through the points. Well, it turns out I can't graph correctly over here. I'm sorry if you were confused by that. This point should be here, and this one should be here. Sorry about that. Otherwise, I won't have my y-axis symmetry. And now the question is, yuck, what is that thing in the middle going to do? Well, I have to make sure I have y-axis symmetry. I have to pass through all the points, and I'm going to stick to the asymptotes. So it ends up being like a parabola. So there would be my graph. I know you're probably thinking gross. These are probably the most intense graphs we will do in this class, just because there's a lot to them. Last example, and then we're done. Same steps. Now with this one though, there's something that should kind of jump out to you. Notice the top is the difference of squares. On these problems, if it looks like something can be factored, I want you to do that first before doing any of the problem, because I'm going to show you what can happen. So I'm actually going to factor the top. So remember the difference of squares, it would break up into x and x, 6 and 6, one of each sign. The whole reason why I did that, because there's multiplication here, the x plus 6's are gone. They can cancel out, and I'm left with just x minus 6, which is going to be simpler to work with than what it originally was. So if you can factor it, do that first. It'll make the problem easier. So let's do the domain. If I look at the original problem, what would have made the bottom 0? Well, if I solved that, I would get negative 6. I do not want negative 6. So there's my domain. Vertical asymptote. For the asymptotes, I would look at the simplified form. Notice in the simplified form, there's no denominator. If there's no denominator, there's not a vertical asymptote. Horizontal asymptote. Well, notice in the simplified form, there's no denominator. If there's no denominator, there's not a horizontal asymptote. I'm sure you're loving this one. We're not going to work with the slant asymptote. X-intercepts. Well, if I work with the simplified form, let's set it equal to 0. And if I solve that, my x-intercept, I get a positive 6. Let's plot that point. 1, 2, 3, 4, 5. So I'm going to touch the x-axis at 6. The y-intercept, I'm going to put 0 in for x. Well, I get negative 6. So 1, 2, 3, 4, 5, 6. There are no asymptotes to draw on this. Now, here's the only kicker with this. Notice x minus 6, that's linear, that's a line. So I can actually make my graph, but I want to show you something that happens with this one. Let's see if I can draw a decent line here. Okay, nope. Will it let me draw a line? Let's see. Okay, so if I draw my line, I'm going to extend it out quite a ways here. This would be my graph, except there's one catch. If you go back to the beginning, I canceled out x plus 6. And we saw that that x plus 6, if I solved it, became negative 6. That's what I had to throw out in my domain. Since I had to throw that out, I do have to represent that on the graph. So all you have to do is go to where x is negative 6, find where the graph is, and you're going to see a hole in the graph, meaning I threw out that one point, and this would be the completed graph. So again, we would say on this one there is a hole at x equals -6. That's what I canceled out. I know it's kind of tricky, but hopefully it makes sense. So I just want to go over one last thing just to make sure we have this down. If I had something like this, x squared minus 5x, and let's do let's change that 5 to a 3. And let's say on the bottom I had x squared minus 16. I would like us to factor this out first. So I know the bottom is the difference of squares. That's going to be this. The top, if I quick factor it, I want to multiply to -4 and add to -3. So I can see that my x minus 4s would cancel. So I want to quick go over these characteristics just to make sure we're good. So here's now the simplified form. The vertical asymptote. What would make the bottom 0? Well, I still have something down there. If I set that equal to 0 and solved, there is a vertical asymptote at x equals -4. Horizontal asymptote. If I look at my simplified form, the highest exponent was 1, the highest exponent was 1. So if I look at the numbers out front, a over b, I have a horizontal asymptote at y equals 1. And now a hole in the graph. The only time I'm going to have a hole in the graph is if I canceled something out. And I did. I canceled something out. So that thing I canceled, if I set it equal to 0 and solved, there is a hole at x equals 4. Okay, so you only have a hole in the graph if you cancel something out.